Ayan, you can start, I guess.
Okay, so I think, yeah, I can start sharing my screen and start it. Okay, so is everything fine? Is the display coming correctly?
Yeah, it is perfect.
Okay,
Fine.
thanks.
Yeah, it's good.
Oh, now I lost my spotlight. Okay, so yeah, so it's a great pleasure now to start our conference and welcome to the inauguration event. So the conference is, as you know well, is the dual mysteries of gauge theories and gravity, and it is virtually at IIT Madras. And if you would have come to our nice campus, which is actually part of a national forest, you would have seen these beautiful creatures called blackbucks. It's an endangered species of deer. And they have these beautiful spiral horns and they have this nice colors. They have different color variations. Some of them are black, some of them are white, some of them are brown, and it's very beautiful. They are really wonderful creatures. But we hope now that this warm invitation, this warm welcome extends far across the seas to all continents where our speakers and participants are from. And so a warm welcome to all of you. And although you are not here, I think our conference would be as intense, as exciting, and as thrilling as the Indian monsoon, which is kind of going on in some parts of the country now. So our conference is essentially in the honor of David Gross, who is here. And he's our guest of honor in the 57th convocation event. So certainly the theme of the conference and is chosen according to keeping this in mind. So very briefly, it's a rather superficial introduction to, and superficial and brief introduction for the sake of people outside of the field who are now present in the inauguration event. So David Gross actually revolutionized our understanding of quantum field theory. Essentially, before his work, it was not even clear that quantum field theory can describe protons and neutrons and and nuclear physics. It was his work that established that the color force that is responsible for quarks and gluons to bind together and form neutrons, protons, and nuclei. It's actually described by quantum field theory, more specifically something called the gauge theory, which is simply a generalization of Maxwell's electromagnetic theory. And this gauge theory is called quantum chromodynamics. It's called the color force. It's like electromagnetic force. And in 2004, he was awarded the Nobel Prize together with his former student, Frank Wilczek and David Politzer. And essentially, they were awarded for showing the asymptotic freedom, which was key to establishing that QCD can describe quarks and gluons. So this thing is called asymptotic freedom. It's a bizarre thing that when you take into account quantum fluctuations in the vacuum, the Coulomb force, unlike the Coulomb force, the force between quarks and gluons actually decreases when they come closer together. The Coulomb force increases as electrons come together, whereas the force between quarks and gluons decreases as they come closer to each other. But this is very important. The work of David is very important in the history of theoretical physics, because I'm just paraphrasing something that David himself said at some other point. I heard him giving a talk at HRI when I was a PhD student there. So great scientific research, not only the greatest product of great scientific research is not actually knowledge, but what we call enlightened ignorance. And this is exactly why David's work is so important, because it pointed out towards this wonderful mystery called confinement, how quarks and gluons actually get confined inside hadrons and we cannot really isolate them. It's the opposite of asymptotic freedom, that the force between these quarks and gluons increases as they get separated from each other. And so you can never actually separate them away. if you try to separate them away, they actually break apart and create more quarks and gluons and more such hadrons. It's still a mystery because we don't really know the mechanism of this confinement, and we cannot describe the structure of protons and neutrons yet. And we are yet to describe this nice, interesting phase of matter called quark-gluon plasma that has been produced by colliding nuclei in particle accelerators and which existed when the universe was just 5 microseconds old. So this is all being pursued. This is one of the major focus of fundamental theoretical physics research today. But David Gross' contribution to science doesn't end there. I mean, he actually co-invented the heterotic string theory, which is actually one of the 5 consistent quantum theory of gravities that we know today. And then since then, I mean, string theory has just grown and grown and has become all encompassing. So string theory, now we know that all these 5 consistent quantum gravities are actually the same theory. And not only that, string theories are also secretly quantum field theories. So quantum gravity in a region of space-time can be described as a normal quantum field theory living at the boundary of the space-time. This is called the principle of holography. And not only that, string theory shows that the deep mysteries of gauge theories and gravity can actually be mapped to each other. So the hard problems in gauge theories can be mapped to easy problems in gravity, and the hard problems in gravity can be mapped to sort of easy problems in quantum field theory. Not that we understand this mapping completely well and how, but in principle, it shows that this can be done. And this explains the logo of our conference. So essentially this is like a Joker smile, where the smile actually is the confinement of quarks. And the other thing, the nose, is essentially showing the emergence of gravity rather than the horizon. Horizon is often shown as a throat, as a long throat. So this is this explanation of the logo of our conference. Anyway, this is rather a brief and superficial introduction of the theme of the conference and also about David Gross. So I'll now have only 2 more minutes. So I'll just say a little bit about the origins of this conference. So when David agreed to become our chief guest of the convocation, we became so happy that we must do something about it. And Mahesh asked us, why don't we do a conference? And he's a dean of international relations now. And this is how it started. But then, of course, it was supposed to be held here and it was supposed to be rather short. But then, because David could be here only for a few hours today. Now, of course, because it's online, we have made it a 5-day conference. And then Professor Raghu, who is now the Dean of Global Engagement, he has given us access to the very new conference facilities, and we are using completely. And of course, there is this big public event coming up, our panel discussion on fundamental physics and society, which would be also, publicity is being done by him also. And we also thank ICS Society Cell for creating website and all the other technical support. So there are certain probably unprecedented things that are happening for the first time because of this conference. Maybe this is the first conference on fundamental theoretical physics of this scale with 44 speakers and happening in any IIT, any institution of technology in India. And certainly, this is probably the first conference where the speakers are listed alphabetically. So you see that the names of the speakers come alphabetically by the names rather than surnames. And this is a great Chennai tradition. And even if you tell, this is something that you cannot undo, because if you tell people to do otherwise, they don't simply understand. I mean, so we thought of just simply following this tradition rather than going counter to it. And perhaps also the first Indian conference where we have David Gross, his student Rajesh Gokakumar, who is now the director of ICTS-TIFR, and his academic grandson, which is myself, I'm Rajesh's student, and my own student, so David's academic great grandson, Tanay Kibe, as speakers, organizers in the same conference. So probably these are the 3 unprecedented things. Well, I have nothing more to add. So thanks IIT Madras, thanks to all speakers and participants all across the seas and across all continents. And of course, we should reserve the thanks to the end. So I simply end by saying that we hope that you will enjoy the conference. And now it is time for David to take over. So over to Suresh, and that's the end.
Okay, so Professor David, maybe you can share your slide. Again, Chennai tradition, call you by your first name.
Of course. So I have no slides. I'm scheduled to speak for 5 minutes. I just would like to welcome everyone to this incredible occasion. So when I was asked to give the convocation address or be the chief guest at the 58th, I think, convocation of IIT Madras in Chennai over a year ago, I gladly agreed and looked forward very much to visiting Chennai at this time of the year. I have very warm memories of my previous visits to Chennai, and I hope to meet old friends. And I was delighted that the organizers planned to have some kind of small conference in connection with the convocation meeting. But as you all the coronavirus came and interfered with these wonderful plans. And so, okay, I therefore felt too bad, maybe next year or some other year, I go back to Chennai. But the organizers were determined not to give up and to so actually I will give my convocation address to the graduates of IIT Madras on the 25th of October. And the small conference that was planned by the organizers, they decided to expand it, take advantage of the fact that we're now used to talking to each other and meeting and over Zoom. Quite a remarkable development, which has been picked up enthusiastically by our community, by the community of physicists and especially theoretical physicists. I don't think there's a day throughout the world where there isn't an interesting talk that you can attend virtually. This might be one of the lasting good effects of COVID-19. I hope there are other good effects. There certainly are many bad effects. So the organizers really have done a magnificent job. I look forward very much to this week. They've put together a marvelous conference, including people, brilliant physicists from all over the world, from 24 different time zones. Not easy to do, but they've done it. We'll see how it goes, but the schedule is very exciting. And as Ayan said, it deals with the most, in my opinion, I think most of us, the most exciting areas in theoretical physics, where the research continues very strongly and independent of the virus that's keeping us all at home, maybe even more productive than before. So I really look forward to the next few days and nights and YouTube recordings that will cover the times where I'm asleep, because some of the talks really look very exciting. And I also look forward to a wonderful event which the organizers have put together and framed, and we'll see how it goes, but it should be very interesting. And that's on October 24th, where we have a public event that will be devoted to fundamental physics and society. So both deep questions in our field and how all science in general, but theoretical physics in particular, relates to society at large. So that should be very interesting at the end of this conference. So I'd just like to end by expressing my deep appreciation to Ayan, who just spoke, to Suresh, and to my new great-grandson, who I haven't yet met, but thanks for, please be welcome to the my growing family of academic descendants. Tane. They've really done a magnificent job. Not easy to organize all of this, to convince people, and hopefully it'll all work beautifully. That's really all I wanted to say. Welcome to everybody, and let's enjoy ourselves in the next and I suppose now I should over to the director of the IIT Madras, Dr. Ramamurthy.
Thank you. So Suresh, should I?
Yes, you can start. Perfect.
Thank you very much. And so normally I'm the common fixture in all conferences that happen on campus. One of the hazards of my job is that I get to inaugurate them. It's useful to me. I get a feel for what's going on. What are the communities that our faculty are part of, and what's the nature of the distribution of people who find it interesting enough to visit the campus and so on. So in the same, though this is a virtual conference, I think in the same vein, I've been asked to participate in the inaugural session. I'm very happy to do so. And particularly, I would like to thank Professor David Gross. He not only has kindly accepted to be the chief guest for our convocation, but we had timed this conference to coincide with that so that we could take advantage of his visit. I think our invitation to him and to all of you to visit sometime later when the pandemic lets us do so is open. We will organize something, I'm sure, to make it possible, so that the physical meeting on our campus definitely will happen if within a couple of years or 3 years, I'm sure. But as David pointed out, this has opened up a great opportunity for people to interact fairly seriously. This is happening in many disciplines. It's happening in academia. It's happening even outside academia, virtually. And because you can do this so easily, it's happening much more. So as he said, it's one of the benefits. It could have happened earlier. Mindsets are difficult to overcome, so it didn't happen with the same intensity and same willingness earlier. I hope this is one of the things that in a hybrid form continues when we get back to face-to-face meetings, which of course have their own value. I must admit straight away that I have no clue what this conference is about. I looked at the title, I read the blurb on the website, and all I can say is the only thing it brings to my mind are the storybooks that I read, the novels that I read as a kid, first Enid Blyton, and then Agatha Christie. The title of the conference looks more like the titles of those books. But they were all exciting books, and there's always this complete mystery about who done it, and here's what's done it. So I think I can share that. I can figure out that I can see that excitement is coursing through all of you. So there's a lot of huge unknowns, and that's what keeps the the adrenaline flowing. So I could see that, and I'm also there's a sort of a small personal connect. I am the university where David is working at University of California at Santa Barbara is my alma mater, because I studied there before he came there. I was there from 1980 to 84. I haven't visited after 86, which is a crime, but I should make up for it. But 88 rather, I visited in 88. And it is, I have very, very pleasant memories of UCSB. So that's my personal connection. It's nothing to do with my role as director. I am glad that such a galaxy of experts on this subject. In the initial powwow before we started, I could see they all know each other. Of course, it's a tightly knit community. I'm glad you all got together, and I can see that the next 4 days, 5 days, very interesting, including this panel discussion that Ayan mentioned. I really have nothing more to add except to say that I wish all of you a fantastic conference. I think while the opportunity that this virtual mode provides for people to gather from across the world, all the people who matter to gather together, which otherwise would be very difficult. The fact that you miss the face-to-face also is definitely a drawback. And so, as I said, the big interesting question will be, how are we going to be creative in taking advantage of both the modes of interaction once we have the freedom to do so. So and when we do that, I'm sure we will, as I said, we'll meet on campus, and maybe we'll find a way to have a physical meeting along with the virtual presence of all the others, all the people who can't come. And that way we've retained some of the benefits of this virtual mode. So I wish all of you a fantastic conference and some meet and greet, whatever is possible over the internet. And as I said, I extend an undated invitation to all of you to visit the campus whenever it's possible. Thank you.
Thank you, Professor Bhaskar. Now I would like to request our head of the department, Professor Sethupathi, who's been an enormous source of support for us, to tell you a little bit about our department. Professor Sethupathi.
Yes. Respected Chief Guest, Professor David Cross, our Director, Professor Bhaskar Ramurthy, local organizers of the conference, Professor Ayan and Suresh Govindarajan, invited delegates, participants, and my dear colleagues and students. As the head of the department, it's a matter of great pleasure and honor to welcome you all to this international conference organized by our department. Our department is amongst the largest physics departments in the country in terms of the number of faculty, students, and the program that it offers, with 50 plus strong faculty conducting research in many frontier areas. Our researchers are engaged in a wide variety of areas spanning the whole spectrum of highly application-oriented research to purely theoretical foundations. The department faculty engage in research collaboration with leading institutions and industries in India and abroad, and also are involved in many national and international interdisciplinary projects such as India-based Neutrino Wave Detection Program, National Solar Energy Program, Gravitational Wave Detection Program, LIGO, collaboration with CERN, to cite a few. The department offers several academic programs with the goal of providing an education that prepares the students with scientific outlook and enables them to solve challenging problems, not only in physics, but also other areas of sciences. In a nutshell, the department has a state-of-the-art research facilities for all the research programs being undertaken to excel in contemporary research and training the students on topics which have a good balance between fundamental and applied component with immediate societal impacts. I'm confident that this conference will fulfill the purpose of creating a scientific awareness on the advances in this field. This meeting is timely and should foster new ideas in the ensuing 5 days of the seminar and discussions. I sincerely wish that this conference will be of great success, not only as an opportunity to share the knowledge, but also a long and fruitful cooperating friendship among the experts in the research area. So I once again extend a warm welcome to everyone to this conference and wish you all a very memorable, pleasant, and stimulating academic sessions ahead. Thank you.
Thank you, Professor Sethupathi. So we are done with the inaugural session, and we still have about 5-6 minutes. So let me just share a slide which has the guidelines for how we should be doing this conference. And can you see this? See the guidelines? So I'll just read the guidelines. These are only guidelines. Please postpone your questions until the speaker pauses to ask for questions or until the end of the talk, whichever is earlier, especially if the question triggers a lengthy and vivacious discussion. Please ask your question only when the session chair allows you to. However, if you want to express strong disagreement or want anything or want to demand anything immediate or urgent clarification, please interrupt the speaker anytime without requesting permission of the chair. Please type out your question at least partially or just outlining it. The session chair will allow you to ask the question yourself sequentially, and you can at the end of the session of the talk, and you can extend your question, of course. If there is any issue with audio quality or connectivity, then the session chair will read out your question for you. Also, if there is less time, the session chair can use their discretion to skip the question too. Okay, but however, Tanay has set up a Slack forum, and you must have all received an email where we want people to start discussing things among themselves, with the speaker, etc., so that there can be collaborations which can ensue from such discussions, and so you can continue the discussions even after the session. And the Slack forum is segmented by sessions, so there will be one forum for each session. So that is the setup that we have, and so that these are the few guidelines. Of course, standard guidelines are that you turn off your video as well as your mic. You keep it in mute unless you want to ask a question. Okay, so hopefully all of you know what to do. And so this just, okay, so let me also now share today's session. So there are 3 sessions every day, and so this morning session, which I am the chairperson, has 2 talks, one by Bern of UCLA and the second talk by Aninda Sinha of IISc Bangalore. And so the duration for the first talk is, if you look at it, 55 minutes, but there is a 15-minute gap, so that it's 55 plus 10 minutes for question and answer. So we've actually put in adequate time for this. Aninda Sinha will be speaking for 40 minutes, and plus there will be again another 10 minutes for discussion. So in all sessions, this will be the format where there will be a reasonable amount of time to ask questions, and so I think the pace will be perfectly fine. So I think now we can get started. At I request Professor Bern of UCLA to start sharing a slide after I stop sharing my share. So you can go ahead and start. I mean, you get extra 2 minutes.
There we go. Okay, just a small technical problem. Sorry about that. So you can see my screen now?
Yes. Do you want me to give you any warning after 40 minutes or anything, or you will be fine?
I have a clock.
Oh, you have? Okay, go ahead. No problem.
It's truly a great honor to be speaking at this workshop. I've always been in awe of David Gross, not just for his amazing science, but also because of his sincere desire to help science throughout the world, including, of course, in India. And I am the director of the Mani L. Baumick Institute for Theoretical Physics. Some of you might know that name, Mani Baumick. But there's something actually I think you'll find extremely interesting about him. And that's that he is, in fact, the very first PhD from the first IIT outside of Calcutta back in 1958. is really amazing. And he has a very interesting life story, which you can read about in his book. But I'll just give you a quick summary, and then I'll tell you where you can meet him. So after his PhD, he went on to first to UCLA, and then he wound up at the Northrop Corporation, where he headed a research group where they invented the first practical excimer laser used in LASIK surgery and in photolithography. But in fact, his basic love has always been fundamental physics, and that began back in Calcutta, where he met Bose and Dirac. And I think Mani is truly a wonderful role model for the young people in the audience. And you can meet him. He will be on the panel discussion, where he will tell you more about the early days of the IIT, and I am absolutely sure he will be delighted to answer any questions you might have. But today I will be speaking about something far more technical, and that's scattering amplitudes as a tool for gravity. So the basic outline is, first I'll explain a little bit about scattering ideas, the modern viewpoint of that. That can be summarized with this little comment: on-shell is good. There's a whole different philosophy of how we think about scattering amplitudes compared to what you read in the textbooks. And the way we do things, it has certain advantages, certain power to be able to do calculations which would otherwise be extremely difficult, if not impossible. And one of the ideas that'll be very important, which actually fits very well with this conference, is the idea that gravity and gauge theory belong together. And that's this idea of the double copy. And it's essentially an idea that the dynamics of the theory is controlled by the same building blocks. And we can see this in perturbation theory very, very well. And then I'll just say a little bit about how to push that out of perturbation theory. And I'll give you 3 sample applications of scattering amplitudes, how it's used, how it's connected to gravity. The first example is going to be with n=4 super Yang-Mills, which if you could evaluate that non-perturbatively or to all perturbative orders, then you can connect that to gravity through the ADS-CFT conjecture. So I'll say a little bit about that, of how that works. And there, I think, some important lessons in that. And then a question which I've spent a lot of time thinking about is the UV properties of supergravity theories. And people have strong opinions about that, but we like to actually check things directly using these methods. And then the final application of these ideas, it's going to be to gravitational wave physics. And there's also going to be other talks, at least 4 other talks by my count, which will be on scattering amplitude related topics. So first, let's talk about some of the basic principles that we use when we think about scattering amplitudes. So first thing is, this is something very fundamental to trying to understand nature. It's that you could say the physics behind the Large Hadron Collider. We take protons, we scatter them, and then the quarks and gluons inside undergo scattering processes that we then interpret. And the subject of scattering amplitudes, it's really a vast subject. And I'm only going to touch on a few points, and especially the ones related to gravity. So one of the basic principles that fundamental to the way we think about scattering these days has to do with thinking about the right variables. So I'll just give you a few examples of this. So this talk will mostly be about gravity, but you'll see by talking about gluons, we're actually going to be talking about gravity, which we'll see in just a few minutes. But anyway, let's consider gluons, a 5 gluon amplitude. So 2 gluons which are locked up inside the proton, they come together, they scatter, and you create 3 gluons. Or actually, not, the gluons aren't measured, but you measure the end product, which are the jets that you see at the Large Hadron Collider. And this would be a typical process that you have to work out. And you can open up your favorite textbook. Peskin and Schroeder happens to be one of my favorites, but whichever textbook you like, and work it out. And this is the kind of thing you get. This is actually a tiny piece of the answer. And you're wondering, oh, what's going on here? Well, the first thing, what this expression represents, it's the momenta and polarizations of the gluons. And this object has to be gauge invariant, it has to remove redundant degrees of freedom, and so on and so forth. And that has something to do with its complexity. But in fact, the problem is we're looking at it the wrong way. We should be looking at it in terms of better variables, helicity variables. It's sometimes referred to as Chinese magic. The idea is with appropriate spinor variables, these are spinor inner products here, with appropriate spinor variables, we can take the same information that was on the previous page and rewrite it in terms of a very compact set of formulas that contains all the information. And then there's another trick that we do. This comes from string theory, where we organize the color in a way that the open string organizes the color factors. And that also helps a lot to disentangle the complexity. Okay, so this is one of the key lessons, you could say, is use good variables. You know, it sounds like a good idea. Now, there's more other problems that you have to deal with, and that's gauge dependence. So generally, gauge dependence is really bad because it's the dependence on the gauge variable, on the gauge choices, that is not physical, right? The gauge symmetry is not a symmetry between physical states. It's a symmetry that removes redundant or unwanted, unphysical states. And the basic problem, if you track it back in the Feynman diagrams, it has to do with something very basic in the way the diagrams are constructed, and that's that you're taking the particles off shell. So the Feynman rules say you have to integrate over all energy and momentum, and therefore what happens is you violate the Einstein relation between energy and momentum. And these diagrams are not gauge invariant. And inherently, we do not want to do that. We want a gauge invariant formalism. And there is such a formalism. One example of this is what's called BCFW, Brito-Kachazov-Feng and Witten recursion relations. Okay, I'm not going to explain in detail how this works, but the essential idea is that the basic building blocks for building up a very complicated scattering amplitude, let's say with n legs that you want to build up, you build up from simpler scattering amplitudes where this intermediate leg is on shell. So this you can think of as some kind of a physical propagating particle. And the information for building the complete amplitude is contained in this recursion relation. You know, how exactly you do that, you know, there's that, maybe I'll just refer you to a textbook. Elvang and Wang would be a good place where they describe the recursion relations in great detail. And the essential part is this new philosophical idea that everything needs to be done in a gauge invariant way. And these methods are extremely powerful and very general. They actually have little to do, or they don't rely on the details of the theory. It relies on Cauchy's theorem, basic facts of field theory, factorization properties, how amplitudes are supposed to factorize on poles, and then these same ideas apply generically to massive theories and also to gravitational theories. But the next step, we're mostly interested in loop calculations, the quantum field theory. And there's another formalism that goes hand in hand with that. Once you have the trees, how do you build the loops? And that we have what's called generalized unitarity method. It's a systematic way of building up higher loop amplitudes starting from tree amplitudes, where these are on shell. Right? So we can think of this as some physical type of object, and we use that to to recursively build up more and more complicated amplitudes. And we're working on shell. There's no gauge dependence. Okay. And this is, I should add, these ideas have had great practical consequences in QCD and collider physics, something called the next to leading order revolution. And we want to apply it to gravitational problems. Well, let's have a look at gravity, at the problem of perturbative gravity. So the way we normally do that, let's say the textbook way, is you start from a Lagrangian, Einstein-Hilbert, you take the metric, you expand around whatever your favorite space is. Mine happens to be flat space, but doesn't matter. You can use any background metric you like. And then the fluctuations are the gravitational field. And you take this and you put it into the Einstein-Hilbert action, and you generate a set of Feynman rules. And what you discover very quickly is you get a very, very complicated mess. I'll show you a little bit of what these vertices look like. And you get an infinite number of vertices. It looks infinitely complicated. And if you try doing these calculations, they're actually quite difficult. Now, let's compare that to another theory that we know and love. My second favorite theory, gravity is my favorite. Second one is QCD. And we look at the vertices there, the 3 gluon vertexes, a 4 gluon vertex. These are a little bit complicated, but nothing like gravity. And there doesn't really seem to be any simple relation between these two. You can compare these two in your favorite gauges, maybe the Donder gauge, Feynman gauge, and you won't be able to see anything. And this actually has, you could say, a very practical problem if you're interested in some computation. Maybe there's some problem you're interested in at 5 loops where we happen to be interested in a problem. And you try to think about what happens if you take the Feynman rules and you try to apply them in some way. You very quickly run into some very serious trouble. It's just from counting. How many terms are there? How many terms in the vertex? How many terms in the propagator? And you just count it up. Let's say you can pick the Donder gauge, but it doesn't really matter how you do it. You can count it any way you like. You can think about superspace, whatever you like. It's really terrible. It spirals out of control. Exponential factorial growth. It looks very daunting. Okay, so let's look at a little more detail. The 3 gluon vertex. Okay, so this vertex we know and love from QCD, and it's a little bit complicated, but it's not so bad. And then here's the 3 graviton vertex, which is hiding a lot of complexity because of this notation. P6 means there's 6 terms in here. There's a sum over permutations that you have to take, or relabelings that you have to take into account. There's a sim here. Remember, the graviton is a symmetric tensor, and you have to symmetrize, and pretty soon you have 100 terms. And pretty soon, if you're a smart graduate student and your advisor says, I have a problem for you, here, start with this vertex, the right thing to say is, I think I want to go work on a different problem. Okay, but in fact, the problem is we're looking at it the wrong way. We need to look at it the on-shell way. These external legs need to be placed on shell. We don't want any gauge dependence in them. So we use Einstein relation. We can use the transversality and the tracelessness of the graviton. Clean it up and you discover something amazing, although maybe it's not completely obvious what to do with it. The amazing thing is that, in fact, the Einstein gravity vertex is the square of the Yang-Mills vertex. So in fact, these two theories really are connected in some way. And this would be the first example of this connection, this comment I made, that the building blocks of gravity are in fact the same ones of gauge theory. Here's gauge theory, here's gravity, same building blocks. So this would be a trivial example of that. And in fact, those modern ideas of how to deal with the scattering amplitudes, the methods, from here, that's all you need to build the entire S matrix. Systematically build the scattering amplitudes, for any number of legs, any number of loops. It's all contained right on this page. If you use the technology that I mentioned before, the way of approaching it, not Feynman diagrams, the on-shell methods. And actually, a very good example of this comes from string theory, these Kawhi-Llewellyn and tie relations. These are obtained by looking at string theory, reading their paper, and then just taking the low energy limit, and you get effective field theory relations between gravity and gauge theory. And you can see that the 4-point, this is a 4 graviton amplitude. This is a 4 gluon amplitude of QCD, I might add. This is QCD at tree level QCD, and this is Einstein gravity on this side. It's really amazing that the actual two theories of gravity, of the Einstein gravity and QCD have this connection. And in fact, you can generalize this for arbitrary number of legs, this idea of recycling, that if we're interested in doing gravity, we don't do gravity, no Einstein-Hilbert Lagrangian, you do gauge theory. And then you appropriately assemble it, you multiply a few things, add things, and out pops on the other side gravity. That's, I think, really cool. Now, one thing I should point out that I still actually find pretty amazing. If you went back to the Einstein-Hilbert Lagrangian, just go back to it, take the Yang-Mills Lagrangian and compare and try to figure out how this can be true. What's the connection? To this day, it's remarkable. To this day, see, it was 1985. To this day, we don't actually have a good proof of that. We certainly know it's true, no doubt about it. There's ways of proving it through using modern methods of recursion and so on. But if you just look at the Lagrangian and you want to understand how the two Lagrangians are connected such that they can have this property, that is very mysterious, even to this day. Now, there's another way of looking at this connection, which is proven to be extremely powerful, and that's this duality between color and kinematics. And that's the idea that there's a relationship between the color factors and the kinematic factors that explain to us how to go between gauge theory and gravity theories. So in gauge theory, we know that the color factors, we know what they do for a living. They're based on a Lie algebra, so they satisfy the Jacobi identity. Well, we can now have a look at the kinematic part to try to understand if there's something analogous. And you can go home and check this. It's actually pretty simple. And at 4 points, this will work in any organization you like. Any type of, you can use Feynman gauge, you can use light cone gauge. It's not going to matter. But what you need to do is you have to get rid of the 4 vertex, the 4-point diagram, the contact diagram. You have to absorb that diagram into the other ones according to the color factor. So if you find the color factor in here that looks like this, let's say S-channel diagram, then you just multiply and divide by S over S, so you have the right propagator. So you just kind of absorb this vertex in here, but you have to put all the legs on shell. That's very important. External legs are on shell. And if you do that, you get an amplitude. You get an amplitude of this form. There's a numerator factor. It's built out of the momenta and polarization vectors. And then there's a color factor. Color factors look just like this. And then there's a Feynman propagator. You can go home and check that, in fact, these numerators, they satisfy exactly the same Jacobi identity with the same signs as the color factor. Now you could say, hell, that's pretty amusing, but what of it? Well, first thing is that this is in fact general. It's been proven in multiple ways that it works at tree level. There's tree level proofs of this. At loop level, it's still a conjecture, but there's plenty of evidence in its favor. And the basic idea is we take an amplitude, we rewrite it in terms of these cubic diagrams, meaning all the contact terms are pushed into the cubic diagrams by multiplying and dividing by any missing propagators. And then the claim is, and this is a proven claim, that there is a way of rearranging this object such that, this amplitude, such that for every color Jacobi identity, there's a kinematic numerator identity. And you'll say, oh, that's pretty weird. That's pretty cute. But what are you going to do with this? Well, let me show you what you do with this. This is the really cool part. So let's do that. We're going to make this arrangement that the color factors of the numerators satisfy the same Jacobi identities. So then there's a little simple prescription. If you want to go from gauge theory to gravity, you take the color factor and you replace it with the numerator factor. So this is something very profound, because what it's telling us now in detail for arbitrary tree-level amplitudes, that there is a deep connection between these two theories. And this is bottom up, that we're just thinking about gravity and Einstein action, and we're thinking about the Yang-Mills action, we're comparing the two. We discover that the detailed building blocks of the theory, the kinematic building blocks, are shared by the two theories. In one, there's a color factor, a matrix, and then a numerator factor. The other one, you get two copies. We call this the double copy. And this definitely cries out for a unified description of gravity with gauge theory, presumably along the lines of string theory, where we think of this as a unified object. And this, you could say, is the echo of this unification in the low energy theory. And in fact, this is quite general. Some of the simple constructions, n equals 8 supergravity. If you want n equals 8 supergravity, you take it n equals 4 super Yang-Mills. Second copy, n equals 4 super Yang-Mills. Maybe you like n equals 5 supergravity, n equals 4 times n equals 1. It looks kind of trivial. Well, it is trivial. If you want n equals 4 supergravity, we take n equals 4 super Yang-Mills, and we'll call it n equals 0 super Yang-Mills, which maybe another name for that is just ordinary Yang-Mills theory. So anyway, it's just a funny name for something trivial. There's no supersymmetry there. And there's actually endless numbers of these examples. It's hard to keep track of them. There's many papers just listing out different supergravity theories and different versions and formal supergravity, et cetera, et cetera. And there's also many other examples which are a little bit bizarre that this should actually work. But let's say Dirac Born-Infeld theory it is related to the nonlinear sigma model through a double copy construction. In fact, we made a little table. This is in our review article, a little chart that links different theories. What these links mean is that they share, we could call it a single copy. So it's like one of the two building blocks. Let's say you pick a supergravity, n equals 8 supergravity. It's built from two n equals 4 super Yang-Mills. And what this line means is there's a connection that one of the copies that's used in this construction is shared by the two theories. So for example, the conformal supergravities, there's a connection to Dirac Born-Infeld theories. So there's this whole web of theories. So you could say a different way of looking at connections between theories through this double copy vantage point. Wherever there's a link, it's clear that these theories belong together because they share like the detailed dynamics, or the building blocks of the detailed dynamics is shared by the theories. So maybe just one comment about non-perturbative, because much of what I'll be speaking about is perturbative. That's where the double copy is well understood. We know exactly what we're doing. But wouldn't it be cool if every classical solution in gravity could be mapped to a double copy of gauge theory solutions? Where do we start? Well, we need to find a few examples. Well, there's an obvious place. We should start with black holes. And in fact, it just works. A black hole is a point charge. It even works abelian. I mean, you really should think about it non-abelian because you need this duality between color and kinematics. But there is a relationship between a black hole, a Schwarzschild black hole, and a point charge, which could be very hard to see, except you have to use the right coordinates, Kerr-Schild coordinates. In these coordinates, then things are much, much simpler and much more obvious what this connection is. The Schwarzschild black hole in Kerr-Schild coordinates, it has this kind of a very nice form, eta mu nu plus phi, so phi is 2m over r, and then there's this k mu, that's analogous to the kinematic numerator. Phi would be analogous to the propagator. You don't double copy that. And in fact, if you look at the solutions, you see the double copy. That there's 2 k's here, 1 k there. As simple as that. Schwarzschild is like Coulomb square. Which is very cool. But there's in fact endless numbers of these things now, where people systematically find new ones. The Kerr black hole, solutions with cosmological constant, radiation from accelerating black holes, maximally symmetric space-times, and so on and so forth. But I should say, there's actually no general understanding. If you take some solution, some arbitrary classical solution, and you try to interpret it in terms of a double copy, that is not known how to do. Each one of these is analyzed case by case. But by now there are enough examples that there's a lot of data that at least guide to figure out a theory behind this. I think some young smart person should look at this. Okay, let me just say a few words about applications of Amplitudes ideas to ADS-CFT. So it's the idea of that by using these on-shell ideas, we can go extremely far. For example, n equals 4 super Yang-Mills theory to all loops. And in fact, non-perturbatively, there's a finite radius of convergence. You do it to all loops. You have planar n equals 4 super Yang-Mills. Of course, the real dream is to do QCD, solve QCD. But that's a very hard problem. N equals 4 super Yang-Mills, as we'll see, that's also a hard problem, but it's much more promising. And one thing is we have ADS-CFT, so we know a lot about what happens at strong coupling. It's maximally supersymmetric, and there's relative simplicity at both strong and weak coupling. In fact, there's a relationship. Scattering at strong coupling and n equals 4 super Yang-Mills is related to classical string theory and ADS space, of course. But if we want to make this link, then you need scattering at strong coupling. That means you have to solve n equals 4 super Yang-Mills exactly. That still seems impossible. Well, how do you do it? Well, usually the trick is you have to be bold. So let me just explain what I mean by have to be bold. So at some point, we did a 2-loop calculation in n equals 4 super Yang-Mills. Now, why we were doing this had something to do with QCD. We weren't doing this was like a little side project. We weren't doing this as a primary purpose, and we were looking at the 4-point amplitude of n equals 4 super Yang-Mills as a byproduct of thinking about QCD. And what we discovered was a little formula that said that the 2-loop is given by the 1-loop square plus some function that had to do with something that was called the cusp anomalous dimension that we recognized. So this function, it's some function that maybe at higher orders we don't know, but we had some good idea of this thing. Okay, so you say, well, that's very nice, but you probably wouldn't be too impressed if I said this, because now what you have to do is take a leap of faith. You have to say, well, if it works now, it probably works forever. Now you'll say, that sounds pretty crazy. Why would you say that? Well, sometimes in physics you have to do that. You have to go well beyond what rightfully should be true, and you guess that it's a possibility. But then you have to believe that it's worth the effort. Well, we had to do a 3-loop calculation in order to verify our understanding. That is rather non-trivial, but anyway, we went ahead and did it. And the long story made short is, based on that, you can guess all of it in one go. At least at 4 points, you can just guess all of it. It's in terms of the cusp anomalous dimension, which by very good fortune had been determined by Bizert, Eden, and Stauddacher. It was the first anomalous dimension that was worked out exactly. So in fact, we knew the exact, based on this guess, we now knew the all loop, resummed amplitude, non-perturbative. Okay. So how do you know it's right? Well, luckily there was Alde and Maldacena. So what they did is they looked at the ADS side, looking at a Wilson loop. It's actually kind of a fun problem. It's the soap bubble problem. You're trying to minimize an area with some wires, and you have to find the minimal area solution. And in fact, we got a match, and that worked very well. And there's some really cool stuff that comes out of this having to do with the discovery of dual conformal symmetry. This is part of what's called Yangian symmetry, and it led to a whole industry of studying that symmetry. But unfortunately, our guess, we guessed it for any number of legs. We just guessed the whole thing. We were partly right. Our guess was correct for 4 and 5 points, but not correct after that. And can we figure out the remainder? So the remainder, when I say the word remainder, I just mean that our guess was wrong. And okay, we'll give it a nice name like the remainder function. And this whole idea of trying to figure out the remainder function, it's a little industry of trying to do that. And it spurred many papers. Lance Dixon is the one who's really been pushing this forward, Lance Dixon and his collaborators. And even though it's quite a bit harder than we thought, we originally thought in one go we'd get the whole damn thing and be done with it. But it's actually quite a bit harder. But the basic idea, the holy grail, what we want, it still looks possible, although it's certainly quite a bit harder, which is to solve for all planar n equals 4 super Yang Mills amplitudes, which then gives us gravity. Okay. Another problem I've been interested over the years is ultraviolet behavior of gravity. This is like a very basic problem. We know various theories. Let's say you know Einstein gravity, you know certain supergravities, and you just want to understand how does the theory behave in the ultraviolet. Okay. So we all know these arguments, non-renormalizability of gravity. And it's based on some very simple ideas, just some simple power counting. What you do is you just observe the comparison of gauge theory, which is renormalizable, to gravity, which is non-renormalizable. The vertices have 2 powers of momentum in the vertex, simply because Newton's constant is dimensionful. It's nothing more profound. Or you could say it's because the graviton is a spin-2 field, and it needs those 2 indices to couple. Right? It's not very complicated. And obviously, if you look at any integral, if you put more powers of loop momentum in the numerator, the integrals are going to have a poor behavior, and the theory will be non-renormalizable. Okay, and that's the basic argument. That's the essential part. But you have to worry about something when you do this. And these power counting arguments, they are based on thinking about pieces which are not gauge invariant, like individual diagrams. And if there's anything we learned from doing amplitudes, is that is a really bad idea. What you need to do is you need to be thinking about the gauge invariant quantities. Okay, and you have to worry about these hidden cancellations. And I don't mean hidden from the theory does what the theory does. It's just hidden from us humans because we don't understand the perturbation theory well enough. And is it possible, it's just a question, is it possible to arrange for an ultraviolet finite quantum field theory of gravity? So what theory are we going to look at? And the answer is n equals 8 supergravity. It's always good to look at supersymmetric theories. It's the best theory to study. It has the best high energy behavior. If we're going to find something, that's probably the place. And also n equals 8 supergravity, if you look at it the right way, it's actually by far the simplest of the supergravity theories. If you look at it the wrong way, it's actually the most complex of the supergravity theories. Okay, let's have a look at where things stand. So over the years, people have been making predictions of where the divergence is. Where's the first ultraviolet divergence? And we can have a look at the scorecard, because certainly I'm of the philosophy, shut up and calculate. That's something that's been attributed to Feynman, although he probably did not say that. So we just want to know what the truth is, and the way we're going to find out is by calculating. And even though I'm going to start making fun of my colleagues, I want you to notice that we're in this list as well. This is back in 1998. We were quite sure there would be a 5-loop divergence in n equals 8 supergravity. And that's in our paper. Well, we were wrong. But pretty much anyone who's made a prediction on this has either been wrong or retracted, or they've been correct, but the way it works is actually not so simple. It has, shall we say, some nuance in it that's actually quite important. I think there's something that has to do with an anomaly here, which is, I think, quite interesting. But in any case, we can just be amused by the fact that the track record of predictions has not been so great. Of course, you could say the conventional wisdom is it says that sooner or later it has to diverge. If not at, let's say, 7 loops, then you might expect it to be at 8 loops, because you're fighting against the dimension, the dimensionful coupling constant. Okay. So I'm unfortunately not going to have much time to go into this, but there was a lot of activity on this a few years ago, trying to figure out what supersymmetry, what duality symmetries say about the ultraviolet properties. And I think the best paper on this is Bjornson and Green in the clarity that they did not need to rely on duality symmetries, because they exposed all of the supersymmetry using Berkovitz formalism. And once you expose all the supersymmetry, that's all the cancellations you're going to get. And what they said is that you're going to find a poor ultraviolet behavior, and I'll tell you in a second what I mean by poor, unless new types of cancellations between diagrams exist that are not consequences of supersymmetry in any conventional sense. So, for example, n equals 4 supergravity to diverge in d equals 4, n equals 5 also in d equals 4, and so on and so forth. There's for n equals 8 supergravity at 5 loops and d equals 24/5. You're going to ask me, what do you mean by d equals 24/5? Well, that's going to be a bit of an issue that I'm going to show you, but it's just done by analytic continuation. You define the supergravity theories in integer dimensions, and you assume some kind of a smooth connection between them. Okay. And then the holy grail, the one we're most interested, is n equals 8 supergravity at 7 loops. And this is the consensus in the field. Okay, we can look at the scorecard. We know a lot of it. Anyway, the scorecard is almost everything is wrong. That means there are cancellations beyond the naive ones you expect from supersymmetry. Okay, except there's an exception. 5 loops, d equals 24/5. There is a divergence there, and the question is, what does it mean? And it's a little hard to interpret, because n equals 5 supergravity at 4 loops in d equals 4, it's finite when it should have diverged. So how can it be that the theory with more supersymmetry, it seems to have a worse behavior? What's going on here? And there's a pretty good clue of what the problem is. it looks like it has to do with our analytic continuation. We shouldn't have done that. What they find, this is Edison, Herman, Martinez, and Trinka. They looked at the unitarity cuts, not a full calculation, and they find that there's extra cancellations. And then we need to go to 7 loops, which is a little bit daunting. But maybe I need to hurry up a little. But the main message from this is these tools are extremely powerful. We can do calculations in supergravity at the same level as people state-of-the-art in QCD. 5-loop QCD beta function, and this is a 5-loop calculation of a similar quantity, an ultraviolet divergence. So a good question is, okay, you got this technology, what's a really nice problem to do? Well, I think we all know what the answer is: black holes. What's nicer than black holes? Black holes are real. So that's, of course, the Nobel Prize from this year. The era of gravitational wave astronomy has begun. And I can tell you, when I started thinking about this, of course, as soon as the paper came out, it said that that for an instant, the event was brighter in gravitational radiation than the power emitted by all the stars in the visible universe are in electromagnetic radiation. And that's pretty cool. Three solar masses of matter were turned into energy. Okay, so oh, and I should also add, of course, Andrea Getz, my colleague, she's had a great influence. She convinced me I need to work on black holes, and that's been going on for years. And I've been thinking a lot about trying to find a good problem on black holes, something that has some meaning. So those of us who are experts on scattering amplitudes, how can we help? Right? What can we do? What does particle physics have to do with the classical dynamics of astrophysical objects? They look completely different. One is, you could say, unbounded trajectory. One involves quantum field theory, QCD, electroweak, quantum field theory. This is quite different. It's a bound orbit. It's general relativity. It's classical physics. But in fact, the very basic principles of effective field theories tell us that there's a connection. And the connection is very simple. If you look at long wavelength radiation from a distance, these black holes, they're just point particles. If they're point particles, we're good to go. And this was actually understood long ago, Iwasaki, and then Goldberger and Rothstein, they systematized this, the whole machinery of thinking about black holes as point particles, and we apply effective field theory. And in fact, I'm going to show you the scattering amplitudes that are ideally suited to push state-of-the-art calculations in gravitational wave physics. Okay, so what's the problem? It's the in-spiral problem. That's what LIGO is looking at, LIGO and Virgo. So the in-spiral problem, we can think of it as 3 parts: in-spiral, merger, and the ring down. Effective field theory is very good for the in-spiral problem. Black holes are points. We take out all our knowledge of quantum field theory, scattering amplitudes. We apply it to this problem. Okay, and the need for extremely high precisions is something very important, because as you're watching the phase of the gravitational wave, the errors accumulate. So in fact, you need high precision. So the way it's done is, the starting point is the post-Newtonian approximation. And the basic idea is you just systematically correct Newton using Einstein's general relativity. The post-Newtonian approximation is done by expanding in Newton's constant and also velocity. And that has to do with the virial theorem, that these things are comparable. And then you can systematically correct it. There's Newton. This is Einstein, Infeld, and Hoffman did the next term. And then over the years, people have been working this out. It's non-trivial, and the reason people do it is because it's important. LIGO measures these things. These coefficients are measured by LIGO. And it's necessary to make predictions or to understand what the data says to do these types of calculations. Okay, so what about scattering amplitudes? So after the spectacular event at LIGO event, people in the scattering amplitudes community really started looking at this problem of the gravitational waves. And the connection to scattering amplitude, there are many papers and different approaches, but the key question is, can we calculate something of direct interest to LIGO Virgo decisively beyond previous state of the art? Well, it happened to be that there was a paper, and the paper told us exactly what we needed to do. I don't think I've ever seen a paper like this with such clarity of what we needed to do. It says, we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. And there you have it. Extremely difficult using standard methods. Trust me, they wouldn't be asking for this if it wasn't extremely difficult. And it's also of direct importance to the people who work on the predictions for LIGO and Virgo. And it also, it's a problem that in principle could enter the pipeline, the analysis. So it's something important for the gravitational wave problem. So what are we after? Actually, I want to just check, is everything, people can hear me? It's okay? Hello?
Yeah, everything is perfect.
Okay, great. Yeah, I was just getting worried. I was talking to a blank screen. Okay, let's go back.
There are a lot of questions we're going to ask you at the end.
Oh, yeah, sure. Okay, so what are we after? So the idea is we want to replace scattering in general relativity with a two-body potential that is easy to use for the bound state problem. We just hand over to our friends who work on gravitational wave physics, and it's ready to go. And what you want to do is you want to extract the physics juice, but you want to leave behind the complexity of general relativity. And the basic idea is to write down a potential, just like Newton's potential, except it has to be compatible with special relativity. That's what this post-Minkowskian is. All orders in velocity. So that's, now this is the preferred way, post-Minkowski instead of post-Newtonian. And that's because you can resum all orders of velocity. And it needs to be valid to third order in Newton's constant. That's what we're after. I'm not going to explain in detail exactly how this is done, but it comes together from two ideas, one from amplitudes, one from effective field theory. We write down an effective field theory, which determines what our potential is, and then by matching it to the gravitational scattering amplitudes of the full theory of Einstein, the real deal, the entire theory, then you can extract these potentials. And this was laid out in a very beautiful paper by Chung, Rothstein, and Solon. We had the technology, put it together, and put out these potentials. Okay, so I'm not, unfortunately, I don't have the time to explain exactly how this works, but there's a, you could say, effective field theory technology for extracting potentials by matching to scattering amplitudes. Now, let me just make a few comments, which are actually great fun. So we very early, we realized that we were in what I'll call unitarity heaven, where we realized that there's a compatibility between the way we like to do things in terms of on-shell quantities and the problem at hand. And the first one is long-range forces. And what that tells you is that you cannot have any contact interactions between, let's say, two black holes. Here's one, oops, should click on it. So this is one black hole, that's another black hole, and then there's gravitons in between. Okay. Now, what that tells you lack of contact terms is that effectively we can extract what we want by putting the gravitons on shell. So these gravitons, effectively, we can think of them as on shell. Then there's another rule that when you're trying to extract the classical piece, you actually have to localize the energy. That's not a surprise because in classical physics, the energy is locked to the momentum. You can't have it just integrated over. So there's another residue here. So in fact, there's this triple cut here. So we were in unitarity heaven, and to do this problem, there are only 3 unitarity cuts that we have to do, and they're really great because there's many legs that you put on shell. Greatly simplifies the problem. And the basic rule is we're going to take these trees, turn them into these loops, just sew them together using unitarity. That's one recycle, and then we take gauge theory. These are obtained actually from gauge theory, these objects, and use double copy, and you get gravity. And just one little example of what it actually looks like. This is at the second post-Minkowski order, so it's order G square. You take a 3-point tree of gravity, 3-point tree of gravity, 4-point amplitude of gravity, and you use, let's say, the Kawhi-Llewellyn tie relations to factorize it into gauge theory. These are gauge theory objects. Same thing that you find in QCD. It's massive scalar. Okay, it's not exactly QCD, but it's QCD-like. Massive scalar. This is a tree amplitude of gauge theory. And the basic input is what I told you. It's gauge theory is the basic input into this. And there's a few technical points of unwanted states and how you control them. That's actually not so hard to do by just controlling the helicities in these unitarity cuts. Anyway, I see that I am running short of time, so let me just wrap it up. Here's the answer as you push it through. Okay, it looks a little bit complicated, but we are at high orders of perturbation theory. This is order G cubed. Newton is hiding in here. Einstein, Infeld, and Hoffman, they're hiding the combination of these 2 pieces, just the lowest terms in the velocity. And this has a certain structure, which has caused endless arguments, I should say, in the literature. Now, you might be wondering, okay, this is very nice, but how do you know it's right? I mean, we certainly caused a commotion in the gravitational wave community. Now, the first thing, of course, is you have to compare to the previous literature. And there's an overlap where you do expansions of velocity, compare the post-Newtonian, and then you have to do canonical transformation. Anyway, we match the previous literature on these, some comparison in an overlap part, and that's highly non-trivial. But that apparently was not very convincing. Our friend Thibaut Damour, he's the one who set us off on this. He was quite certain our results were wrong. I think those of you who know Thibaut know he's quite sure of himself. So I could not resist. I had to, of course, make a bet with him on that. And he had some specific corrections. If you're curious what it is, you can look at it, version 1 of his paper. But anyway, we're done. There have been calculations, a new set of calculations, also by Damour himself. There it is. He did the hard work so he could pay me a bottle of wine. But anyway, there have been multiple calculations that support that we did is correct. So okay, maybe it's not 100% guarantee, but it's pretty darn good that we passed highly non-trivial checks and some careful scrutiny. Okay, and I think the most exciting part of this is the ideas are far from exhausted. This basic idea of looking at gravity in the on-shell way, we look at it as through the double copy. It's got legs. It's going to go a lot further. I think it's just the beginning. And there's many problems to be looking at. Of course, higher orders, resummations, thinking about resummations. Okay, that maybe the BDS ansatz is not a good example, but something like that, we should really need to examine. Remember, we're doing classical physics here. So the possibility really is open that something like this could be done. There's the working on the radiation part. So this is the conservative part I was talking about. Radiation is done separately because there's actually a separation of scales you can take advantage of. But that's a very good problem. A lot of people are working on spin and tidal effects. In fact, just tomorrow, you'll see on the archive, FTH will have a paper out on that has to do with tidal effects. It turns out you can do extremely high orders in the tidal effects, very high power operators for the tidal effects all in one go. This is pretty cool. Anyway, the bottom line is the amplitudes of the double copies. It's having a real impact on gravitational wave physics, I think. And I think we can expect many more advances. Just to wrap it up, I seem slightly over time. The scattering amplitudes, it gives us a new way to think about the problems of current interest in gravity. The double copy gives a unified framework for gravity and gauge theory. And it's something that we can apply to a variety of problems. Talk about various applications. This web of theories is actually pretty interesting. I think the way the different theories are connected through the double copy. There's the classical double copy, the non-perturbative one, high orders of explorations of supergravities, and especially looking at the ultraviolet, but just classifying supergravity theories, I think is something very interesting. And then Hamiltonians for gravitational radiation. And in final summary, I think we can expect many more advances in the coming years, also more generally for understanding gravity and its relation to the other forces through the double copy. And if you want some further reading, there's a review article, and there's also our long paper on how we did the gravitational radiation problem. Gail, thank you.
So there are a few questions which are there in the chat. I'll just call out the name and the person can ask the question. And so we start with Bindu sir, who had a couple of questions. So Bindu, please go ahead.
Yeah, thanks, Suresh. Yeah, hi, Zui. So yeah, I have like a couple of questions. I mean, I'll ask them in the order of my priority. So my first question was about this n equal to 4 supergravity. So if I understand correctly, it is finite at 3 loops, but divergent at 4 loops.
That's correct, yes.
And the divergence at 4 loops is related to the U1 anomaly.
Yeah, right. Well, I made a comment that has something to do with an anomaly. Yeah. And the format of the divergence or the origin of that comment has to do with the precise way it appears. So anomalies in dimensional regularization, they always appear as epsilon over epsilon effects. Yeah. Right? And this divergence is exactly of that form. It's an epsilon over epsilon times 1 over epsilon. Okay. And there's an interesting paper from Bardeen where he connected this to an anomaly. This has to do with self-dual field theory.
Yeah. So my question was regarding the existence of this candidate counter term, which can remove the anomaly. So will it have any effect on the 4-loop divergence?
Well, we happened to write a paper about that. So in fact, we did figure out a counter term that removes the anomaly. However, it requires some real work to feed it through. So you have to, I mean, it's a simpler calculation than a 4-loop calculation, but I think it's, if I remember, it's a 3-loop calculation that has to be done. So there's some real work that has to be done to try to understand exactly what the consequences is. But we wrote a paper that suggested exactly what you're saying.
Yeah, right. Yeah. Okay. Yeah, thanks. Second question was, is there a double copy for n equal to 3 or n equal to 2 supergravity in 4 dimensions?
Oh, yeah. Oh, heck yes. So the double copies of those theories tend to be more complicated. So I actually, offhand, I don't know the paper, but you should look at papers from Johansson, maybe Roybon,
Okay.
on the lower supersymmetries.
Mm-hmm. Okay.
Those constructions are more complicated.
Mm.
But
Okay.
as far as we can tell, every supergravity that you could come up with is going to have a double copy, but there's no proof of that statement.
Mm-hmm. Mm-hmm.
Okay, so next question is from Ayan.
Hi, Zivi. Thanks for this wonderful and exciting opening talk.
Thank you.
I have a question which is being an outsider of a field. I'm a bit outsider, so I'm probably a bit vague. So I wanted to ask if what is known about this double copy at the loop order, and does it require the supergravity that you are producing by this double copy has some that there's certain counter terms you cannot write down, or some property of UV divergences that you require for such a double copy to exist in general beyond the.
Yeah. So, okay, maybe I'll present what's known. So, we actually had enormous trouble building a double copy at 5 loops. We were actually never able to do it. But what makes it extremely tricky is that when we build a double copy, we impose other conditions to help us do the construction. We might impose that the diagrams have a certain kind of locality, or maybe they have some kind of symmetry, that they manifest crossing symmetry, or they manifest a certain power counting. And the only thing we know is that it's actually not completely straightforward to build double copies at very high loop orders. Okay, so there's no proof. Well, we don't have a proof that it can be done or that it can't be done. It's just difficult. The direct connection between counter terms and let's say, like, you use the double copy idea to restrict the counter terms directly. That we don't know. We certainly looked for that, because that would have been a very fast way to get at the answer. If you could prove that, let's say, certain counter terms violate some property that you believe is there, you could somehow use that. But we were never able to, shall we say, put on strong enough restrictions on counter terms directly from the double copy idea. And some of this has to do with, well, there's actually, maybe we could talk in the Slack thing. Maybe it'd take me a while to explain about the issues. But anyway, we have tried and we have not succeeded to impose direct constraints on counter terms, straight out of double copy. And the rules for doing that are not completely obvious.
Thanks. So is the string theory embedding going to help? Like, that if the supergravity can be obtained from the string theory, then will it help to understand this double copy business as a product of 2 open string theories, something like that?
Well, the fact, okay, well, the earliest constructions, like, let's say n equals 8 supergravity, the fact there was a well-known type 2 string that told us exactly what was going on, that made life a lot easier, armed with the Kawhi-Llewellyn and Tai paper. But at least right now, these double copy constructions have taken a life of their own. There's all sorts of examples where it's not at all obvious how you're supposed to embed it in a string theory. I mean, maybe I don't understand what you're driving at. Like, is it in terms of the ultraviolet properties, or just understanding the double copy? What's definitely true is if you have a string theory, then it's very simple to see how the double copy works. Basically, it's the Kawhi Llewellyn and tie paper will then tell you.
Yes, I mean, string theory anyway doesn't have this UV divergences. This is why I was saying that maybe one can directly help to see this double copy at work from the string theory amplitudes itself.
Do you mean in terms of understanding the ultraviolet, or do you mean just or do you mean like proving?
I think we should move this discussion to the Slack so that other people's questions can be.
I think that's a good idea because
okay, sure.
Okay.
I'm not answering well since I don't actually understand the key issue.
So next person is Angelo Fazio. Please ask your question. Okay, I don't see a response from Angelo. So Arpita Mitra, can you ask your question, please?
Yeah, so my question was like, if we are considering unbounded trajectories for a probe mass scattered in a black hole background, so in that case, we will not be able to replace this scattering with a two-body potential. So like these techniques, can we use that?
Oh, wait, sorry. I missed the first part of your question.
Yeah, like,
can you repeat the question?
Like if I'm considering a probe mass scattered in a black hole background, which is following a unbounded trajectories, then can we replace this scattering with a two-body potential kind of a stuff? Like we can use these CFT techniques. Like if we're considering unbounded trajectories, not bounded trajectories.
Right. So the whole secret of the matching is once we extract the potential, then we are good to go. It's just a Hamiltonian. You're done. You can apply it to any problem you want. So we do the problem for unbounded, extract the potential, and then that object is fed to LIGO. The potentials, Hamiltonians, potentials, that makes them happy.
Okay.
So solving the unbounded problem is good enough, but you have to put it in the right format. It also turns out if you know the scattering angle, you're also good to go. But that's another story.
Okay. Thank you.
Okay, so the floor is open for one question from somebody, from anybody.
Yeah, I had one more question, if I can ask.
Yes.
So what is the relation between this off-shellness and gauge dependence? I think I didn't understand that part.
So if you let's say you go to Peskin and Schroeder and you follow the Feynman rules, you'll find every Feynman diagram is gauge dependent. And then you'll find the sum of Feynman diagrams until you go on shell. You just computing green functions. You'll find that that's also gauge dependent. And it just literally depends on the choice of gauge. You work in a different gauge, you get a different answer. The two answers will only agree after you go on shell, and if you're at loop level, you also have to renormalize. But the on shellness is something that you do not find in Feynman diagrams. It's just not the way it's done.
Yeah. So basically, you're talking about external legs being on shell or off shell, right?
Indeed.
Yeah.
Yeah. So the way the objects are constructed is by taking the internal legs on shell and using that to construct an object equivalent to what you would have gotten from Feynman diagrams. It's exactly Feynman diagrams, except you put now the external legs on shell, right? So the on shellness is used throughout the calculation, inside, outside. The final product is an object completely equivalent to a Feynman diagram with its external legs, like you said, on shell. And that object, after a normalization, is gauge invariant.
Okay, thank you.
Okay, so let's thank Zvi for a wonderful talk. And
thank you.
speaker is Aninda Sinha, and he'll be sharing his slides, as you can see. He's going to talk about rebooting the S matrix bootstrap. Aninda, you have 40 minutes plus 10 minutes for questions at the end.
Thank you very much. Can you hear me?
Perfect. Everything is perfect.
Can you see my pointer?
Yes.
Thank you very much. So let me begin by thanking Suresh, Ayon, and Tanay for organizing this wonderful workshop. So I'm going to talk about rebooting the S matrix bootstrap. So you heard from Ayon something about David's descendants, some of whom are new to him. So you'll also hear about some of David's ancestors in this talk. So the idea of the S matrix was first proposed by John Wheeler in 1937. And this was, for a while, it was dealt with in several papers by the founding fathers of quantum mechanics and quantum field theory. In particular, this was highlighted by Werner Heisenberg in 1943. It's peculiar historically that this was during the time of the World War. And then in the 1960s, this became the S-matrix bootstrap program, primarily of Jeffrey Chew's. The idea was to do away with the problems faced by perturbative quantum field theory, and in a more sort of radical fashion to do away with the quantum field altogether. So in the 1960s, this program was advocated by a number of people, primarily by Chew, but also by Mandelstam, Lehman, Martha, and many others. And the underlying principles of this program, behind this program, were very basic properties like Lorentz invariance, unitarity, analyticity, and also very importantly, crossing symmetry. And of course, the question is if these conditions are strong enough to give us a theory uniquely. At that point of time, they were searching for a theory, consistent theory of strong interactions. So whether it would give it uniquely, it's of course a very important question to understand. In recent times, it makes sense to rethink or try to reboot this problem because of the successes that the conformal bootstrap program has faced. So in particular, from 2008 onwards, there is a lot of activity in the conformal bootstrap, not only trying to develop better numerics, but also to understand how to do conformal bootstrap analytically, some of which I've been involved in. But the main motivation is the success that the numerical techniques that are available right now. And the question is what mileage they can give us if we apply the same numerical techniques for the S matrix bootstrap. So here, this is one of the well-known plots in the numerical conformal bootstrap. So this is on the x-axis, you see the scaling dimension of the fundamental scalar, and on the y-axis, you see the scaling dimension of the leading scalar operator that appears in the operator product expansion of two of these fundamental scalars. You can do it for theory with global symmetries, and you start getting constrained regions. So below these lines, theories are allowed. But the most important property of this plot that you should remember is this special feature, this kind of a knee or a bend or a kink that appears. And these interesting theories that we know from our studies, say from the epsilon expansion or Monte Carlo techniques, tells us that the interesting theories like the Ising model, the O2 model, and so on, they all reside at the kink. So the kink is going to play some kind of a major role in my talk. So since this conference is in the honor of David Gross and I wanted to appear intellectual, I Googled David Gross bootstrap. And I learned that his advisor was Jeffrey Chew, who was the main proponent of the bootstrap in the 1960s. But more interestingly for me, David wrote a paper in 1967 entitled Bootstrap of the Rho-Regge Trajectory. Now, this is a huge coincidence since my talk will feature both the Rho and the Regge trajectories in a crucial way. So my talk is based on a paper that we put out recently in June this year, with Anjishnu Bose, Parthiv Haldar, Pritish Sinha, and Shashwat Tiwari. So Anjishnu, Pritish, and Shashwat were my undergraduate thesis students. Parthiv is my graduate student. And also, this is also based on a work that is going to appear very soon, hopefully, with Anjishnu and Shashwat. And they are extremely hardworking undergraduates, and all the numerical works that we have done that I'm going to present in this talk were done by them. So the S-matrix bootstrap was sort of rebooted in these couple of papers, or there was a series of papers by my academic brother Miguel Paulos, Joao Penedones, Jonathan Toledo, Balt van Ries, and Pedro Vieira in 2016, and it was applied to the context of pion scattering amplitudes in 2018 by these gentlemen here. But it is fair to say that this program is not as well explored as a conformal bootstrap. And what I'm going to report builds on these papers in an interesting way, and we'll also see how to take it forward. So the outline of my talk is that I'm going to begin by reviewing bootstrapping quantum field theories, and then I'm also going to review some background that is going to be essential, which deals with pion scattering. Then I'm going to tell you about the allowed space of S matrices. So like what you saw in the conformal bootstrap numerics, there was an allowed space of conformal field theories. We'll also get an allowed space of S matrices. The primary focus in that allowed space of S matrices will be which of these S matrices give us good scattering lengths, which give us good resonances, which agree reasonably well with experiments, and also which of these S matrices exhibit Regge behavior. And then in the third part of my talk, I'm going to turn to the question, what is so special about the standard model? So you'll get a space of S matrices, and the standard model will correspond to a region or a point in this space. But what is so special about this? And can we think of, or can we investigate if there is a selection principle that selects out the standard model? So let me begin with the first part of my talk, which is bootstrapping quantum field theories. So here is some lightning review about pion scattering. So we really cannot make pions in a lab and scatter them like you can do with protons in the Large Hadron Collider, but we can study this process indirectly. And there's a lot that is known. Experimentally, there's quite a bit that is known. The reason why this is a favorite process for theorists to study is that a lot of axiomatic quantum field theories studies, like the high energy bounds, like the famous Frossard bound, can be investigated for this problem. And the main reason for this is that this process has a simpler analytic structure in the complex S-plane. Phenomenologically, a lot is known about light mesons. So the pions, of course, you know that they have, in terms of the mass of the pions, they have a finite lifetime, so they'll have an imaginary part, but the imaginary part is small compared to the real part. So we can imagine that the pions are close to the real axis, or literally on the real axis if you want. Some things are known about the resonances. So for instance, the rho meson appears as a resonance. It has a reasonably sort of big imaginary part, so it will be away from the real axis. And the higher spin resonances are also known up to spin 6. The error bars increase as you go up to spin 5 and spin 6. The spin 1, the rho meson resonance has reasonably tiny error bars. So if we wanted to use any of these resonances as an input for the bootstrap program, we will use a rho resonance. This scalar resonance, the spin 0 resonance, is quite controversial. It was first proposed by Schwinger in the 1950s. But so far as the phenomenological status of this sigma, or the F0 500 meson, as it is called in the in PDG now, it's still a bit controversial. The error bars are quite big. And also the one thing to notice is that it does not have a Bright-Wigner form. It has a large imaginary part, so it cannot be thought of as a Bright-Wigner resonance. So we will see what the bootstrap can say about the F0 500 resonance. But the most famous property that we usually associate pions with is that if you plot the spin versus m square, you get this famous Frucci plot, and you get almost straight lines. The resonances almost appear to lie on a straight line, and this, of course, was the precursor to string theory. So theoretically as well as experimentally, few things are known about scattering lengths as well. So these are low energy properties about the scattering amplitude. The main things that you should keep in mind are these spin 0 and spin 0, isospin 0 and isospin 2 scattering lengths, which are known theoretically using chiral perturbation theory for a long time. As well as they are known up to a certain error bar using from experiments as well. So our focus will be to see which of the S matrices we'll get from the S matrix bootstrap, how close they give us these values. Okay, so just so that the notation is clear and everybody is on the same page, let me just quickly review some basic kinematics. So I'll be considering 2 to 2 scattering. It might be pi 0 going to pi 0 pi 0, or pi plus pi minus going to pi plus pi minus, or any of these combinations. I'll be using standard Mandelstam invariants, and the scattering amplitude will be expanded in a partial wave expansion. These F sub L's are the partial wave amplitudes. PLs are the standard Legendre polynomials. And unitarity gives us this constraint that the mod of FL square should be less than the imaginary part of FL and should be less than 1. See, the analytic structure of the amplitude is quite simple. So if we go to the complex S plane, then there is a cut from S equal to 4 and corresponding U channel cut on the left side. In principle, there could also be poles on the real axis corresponding to bound states, but in the problem that we are going to consider, we'll assume that these are absent because we'll consider that there are no exchanges like, say, photons or any massless exchanges. We'll assume that they are not there because we'll be interested in the strong interaction side of the problem. And of course, a lot was people tried to get a mileage out of this analyticity properties in the 1960s, and there was a program called the analytic S matrix that was quite popular at that point of time. So imagine that you started off with this amplitude and you wanted to impose crossing symmetry. Then you'll get some equation that looks like this. And then suppose you just wanted to expand this in the partial waves, and then you wanted to solve it. Then immediately you'd have problems because it would be hard to solve. One of the reasons is that imagine that you have a resonance which would correspond to a particular pole, a complex pole. Then in order to reproduce that on the crossed channel side, you would require to resum an infinite number of spins because these are polynomials in the crossed variable. So if you have a pole in S on the right hand side, you have only polynomials in S, so you'd require to resum everything before you get information about that pole. So instead of doing it this way, what we'll do is change the basis for expanding the amplitude. So what we're going to do is first map the cuts onto a disk onto the boundary of a disk using a conformal transformation. Rho S gives you a new variable, and the cut structure is manifest here. So the S equal to 4 cut is mapped on the boundary. You can in this conformal transformation, you can choose your S0 to be anything that you want, but it's convenient to specify a crossing symmetric point. So we'll choose to use S0 equal to 4/3 m square. And then the idea is that you're going to expand your amplitude in terms of this new variable, but in a manifestly crossing symmetric way. So alpha, ABC are parameters, and you're raising rho S and the corresponding T and U variable rho t and rho u to various powers, and that will give you a bunch of parameters. So we'll impose the symmetry property so that this expansion is manifestly crossing symmetric. And then what we will do is we are going to check for unitarity. So we will ask, starting with this amplitude, we will impose this unitarity condition, which is a nonlinear condition, and it would appear to be quite difficult to impose even numerically. But quite remarkably, these conditions can be recast into a semi-definite programming problem. And the semi-definite programming techniques were what people had developed over the last 10 years for the conformal bootstrap program. And so that is why you can recast the S-matrix bootstrap numerics into the same problem that you solved for the conformal bootstrap. So here is what you would do numerically. You would impose unitarity, and unitarity would give us constraints on what these parameters alpha, a, b, c would be. And then, of course, the next you have to ask the right question. So you have to give some inputs and then ask what you get out of it. So a bit of theoretical background so far as what is known about pion scattering to chiral perturbation theory. So chiral perturbation theory is an effective field theory. It was first done by Weinberg and then developed by a lot of people, most notably by Gasser and Leutwiler. And because it's effective field theory, if you wanted to do tree level 1 loop and 2 loops, you have to give more and more experimental inputs to fix various unknown constants. So what you get is you have 3 kinds of isospins, isospin 0, 1, and 2. And for each of these isospin projected amplitude, you can do a partial wave expansion, which is labeled by the corresponding isospin as a superscript. So Weinberg showed that at leading order, the isospin 0 and isospin 2 would have zeros. And the zeros would occur at the values s equal to half and s equal to 2. So the isospin 0, I will subsequently call it as S0, and isospin 2, 0, I'm going to refer to as S2. So there are these zeros which correspond to S0 equal to 0.5 and S2 equal to 2. These are called Adler zeros, following Adler's work using partially conserved axial currents. And these zeros should exist not only at leading order, this is a leading order result, but also at subsequent orders, so they should exist non-perturbatively. So if we wanted to set up this problem using the bootstrap, what are the ingredients that we would put in? So we would need to demand that there are some Adler zeros in the S0, S2 plane. But to make progress, we'd also need to put in some input, some phenomenological information. And the input that we are going to use is the rho resonance. We are going to put in the known value for the rho resonance. In my units, it will be at 5.5 minus 0.5 times an imaginary I. So when you do this, you need to find out what values of scattering length you get. So scattering lengths are defined by expanding the real part of the partial wave amplitudes in this way. So the scattering lengths are the leading part of this expansion. And the subleading parts also carry physical information, and they're called effective ranges. The experiments give us results for the scattering lengths. Less is known about the effective ranges, although theoretically, including chiral perturbation theory, we can calculate these effective ranges as well. And you can also say something on the lattice about the scattering lengths. So our inputs for the bootstrap, which will be somewhat different from what was originally used by by Penedonis and company, is that we are going to use some D-wave dispersion relation inequalities. So we're going to assume the Frossard-Gribov representation for the scattering lengths, and we will get certain D-wave inequalities, which will put some sign constraints on combinations of the scattering lengths. And we are also going to put in some sign constraints for the S waves. The S wave inequalities do not have a dispersion relation based arguments to give you these constraints. Rather, what we're going to do is we are going to assume that this has a Lagrangian description, and the Lagrangian description gives us some constraints on the signs. So this is where these S wave inequalities will come from. And we are going to impose a row Meson resonance, and then finally we are also going to impose unitarity. Then we will see what kind of S matrices we get. So this is going to be the inputs for the bootstrap. So the questions that we're going to probe are, which of these S matrices that we'll get match with experiments? Do we see Regge behavior anywhere? And more interestingly for us, to make connection with the kind of things that were found in the conformal bootstrap, are there any special kinks, any geometric features about these plots? And does the standard model live anywhere near these kinks? And if the answer is yes, what is so special about these S matrices? Why should the standard model live near the kink? So we are going to benchmark our expectations. So we are going to find an allowed space of S matrices on the Adler0 plane. So S2 is the isospin 2 Adler0, and S0 is the isospin 0 Adler0. So the crosses here are what follow from chiral perturbation theory. The black cross is the tree level value. The orange cross is the one loop value, and the red cross is the two loop value. Two loop is the state of the art for chiral perturbation theory. People haven't gone beyond that. So these are very close to a particular region on the S2 S0 plane. And the second thing that we're going to do, because we are string theorists, or many of us are, is we're going to see what the famous Loveless-Shapiro model, which is supposed to describe the pion scattering problem, what that gives us. So this Loveless-Shapiro model, you can ask me later on if you have any questions. I can show you explicit formula, but you can do a phenomenological extension for this Loveless-Shapiro model and extend it to the so that it has arbitrary Adler zeros. You get a line of Adler zeros for the Loveless-Shapiro model. The green region here on this line gives us good scattering lengths which match with experiments. And as you can see in the zoomed plot, that this line of Adler zeros for the Loveless-Shapiro model separates out the tree level from the one loop and the two loop values. Another thing that is worth mentioning is that these models, these S matrices corresponding to the Loveless-Shapiro models, are not unitary. This is a nice exercise to work out to show that they are not unitary. In fact, if you wanted unitary amplitudes in 4 dimensions, you will get some Adler zeros here for negative S0 and S2 close to 4. So these are the two benchmarking things that we'll keep in mind: the chiral perturbation theory values for the Adler zeros and this line that corresponds to the Loveless-Shapiro model. So before I proceed, maybe I can pause for a minute and ask if there are any questions so far as the background is concerned.
This line, is it like a bound, or it's an exact? I mean,
no, this is an exact result.
On the line.
Yeah, this is these Loveless-Shapiro models lie exactly on the line. So okay. Yeah, so this is a line of Loveless-Shapiro models.
Thank you.
Okay, so let's proceed and tell you what we find if we do the S matrix bootstrap numerics. So what we will get is a river of S matrices, allowed S matrices. So what we'll get is this. So you'll get a river of S matrices. So the region in blue are allowed S matrices, which are compatible with the conditions that we impose. So the conditions were, just to remind you, there were these D wave inequalities, the S wave inequalities, the row resonance, and unitarity. So all of these together give us this line. So there are two banks. There's an upper bank and there is a lower bank for the river. And this brown line is the line of Loveless-Shapiro models. These crosses are the chiral perturbation theory Adler zeros. In the main plot, I've just exhibited the two-loop chiral perturbation theory Adler zero. The green regions give you good Regé behavior. So the green regions, there are two green regions. So there is a green region here, a tiny green region close to some bend in the river, if you want to call it, and you can zoom in and you can see that there is indeed a bend in the river. It's also a point where the Lovelace-Shapiro line appears to intersect the river. But more interestingly, there is another region here close to the bottom, to the second boundary, where the Lovelace-Shapiro line also intersects, but which also has good Regé behavior. In fact, it'll turn out that the S and P wave scattering lengths here are going to be reasonably good. What will not be good, what will differ from the A region and the C region are going to be in the effective ranges. So the effective ranges in the C region are going to be very negative, whereas in the A region will be closer to chiral perturbation theory. But anyhow, so this is called the river, and this is what you find. You get a river. So when you get the river and you focus on, say, the A region and ask, do you get good Regé behavior in this region? The answer turns out to be yes. So you again do this Chu-Fracci plot for the resonances that you get in this region. So there are in a neighborhood of this kink type region, which is near here. So there's a bunch of S matrices which has good Regé behavior. So the green dotted line is what you get from experiments, and the other lines are the best fit lines that you get from the considering the S matrices that lie close to that kink. Also, quite interestingly, you do get the spin 0, the F0 500, which I told you is controversial in the literature. Only recently there is some agreement as to whether it exists or what the values are. And I'll show you what the F0 500 that we get from these S matrices will be in a bit. Now, the reason why you get disallowed regions, so here you have a white region, these are all disallowed regions. And the reason why you get disallowed region is because suppose you were looking at the maximum of the partial wave, the isospin 2 partial wave, and the minimum of the isospin 2 partial wave. It turns out that the maximum and minimum have the same sign, so they both become negative in a region of the S2. So here I have fixed S0 and I'm dialing S2, and I'm looking at the maximum partial wave coefficient and the minimum partial wave coefficient. So if they have the same signs, you will not get a 0. So that particular point S0, S2 will be ruled out. So this red region will correspond to a range of S2 which will be ruled out. So that is what gives us allowed regions. So you'll get white spaces, and that is what will give you blue regions, which will correspond to good S matrices. So you get this emerging sigma meson of the F0 500 also, and you get a good sigma meson, especially near this kink. So this A region is what I'll refer to as the kink. You also get good sigma mesons here in C, so keep that in mind. Here I'm showing you the plots of the kind of partial wave behavior that we get near the A region. And as you can see, all of them look more or less similar. And if you plot the value, the real part of the resonance as a function of S0, and then you compare with experiments. So experiments gives a big error bar. So experimentally, if you look at PDG 2018, it gives you the range of the real part to lie between 400 and 550 MeV. And as you can see that there are a few S matrices which respect that property. Now, not all of these S matrices will have good Regé behavior. In fact, only a few of these S matrices also have good Regé behavior in addition to exhibiting the F0 500. And all this happens near the kink. So the question is that, okay, you have got these allowed S matrices, but how do you know whether it's, how do you quantify whether it is close to the actual expected standard model results? So one thing that you can do is you can compare it with the chiral perturbation theory results. You can ask these S matrices that I've exhibited here near region A and these S matrices that I've exhibited here in near region C, how close are they? And by close, I don't mean you measure the distance on the S2S0 plane, but you have to do something different. How do I quantify whether these are close to the red cross? So to quantify this, we use a quantum information theoretic idea, which is called quantum relative entropy, which gives me an idea about the distance between two density matrices. So you can compute a density matrix for the S matrices in region A. And so you compute a reduced density matrix by tracing out one of the outgoing particles in momentum space, and that will give you a density matrix, reduced density matrix in region A. And then for so that you use for row 1, and for row 2, you use the same reduced density matrix, but for the chiral perturbation theory point, which is the red cross. So you can now compute this and then ask which of these theories are actually close in this sense, in the sense of the quantum relative entropy to chiral perturbation theory. So this is called hypothesis testing. So relative entropy is used to do hypothesis testing. So if you have two competing theories, T1 and T2, which give you two different probability densities, then with what confidence can you say after n measurements that these are different? And this is actually governed by 2 to the power minus n. So n is the number of measurements times the relative entropy. So this actually tells you that larger relative entropy is the fewer measurements it will take to reach a particular set confidence level. So when you do this, there's some math involved. It's not very complicated. So in fact, you'll get a nice equation in terms of probability densities. Probability densities. Here it is. M is the amplitude, and you're taking mod square. X is cos theta. So there is some way of converting into angles. S is the usual Mandelstam variables. Gx is mimics the detector. So you have a detector at an angle x. So you can think of this Gx as a Gaussian distribution centered around x. So when you do this, you get quite a number of these S matrices to be close in the sense that they give you approximately same values. Same kind of closeness to chiral perturbation theory. So there are S matrices on the upper boundary as well as on the lower boundary. And there are interesting S matrices near the kink as well as in the lower region. So you remember that I was saying that there are two interesting regions which somehow give good Rege behavior as well as good scattering lengths. And so that there is one region here close to the upper kink, and there's also one region here close to the lower kink. So now that brings us to the question, why standard model? So is there some special thing that happens near these kinks? So what we find is the following. And this is kind of motivated by what Mandelstam told us in these physics reports, dual resonance models. So what he said, and I'll read it out for you, that the more ambitious workers in the field hope that the dual resonance models may form the basis of a new approach to hadron physics. The narrow resonance approximation may be regarded as a kind of weak coupling approximations, since if the resonances are narrow, all decay times are long, and all scattering amplitudes are small. What happens is that if you look at what the total scattering cross-section does as a function of S0, so S0 is the isospin 0 Adler 0, you will find that the total scattering cross-sections exhibits a very sharp dip near the kink, near the A kink. So as you are going along the river, So let's show you this river. So if you're going along this river, you will find that suddenly here near this region, there is a very sharp dip in the total scattering cross section. So this is what this plot is showing us. On the y-axis, I'm plotting the derivative with respect to S naught. S naught is a parameter in the space of S matrices. Sigma bar is an average total scattering cross section. So what I'm doing is I'm averaging the scattering cross section, choosing some upper cutoff. And each of the, irrespective of these cutoffs, there is always a very sharp dip at more or less the same point. And this is what the zoomed in inset is telling us as well. And that is a location. So this is a measure of where the kink is, what I've been referring to as the kink, because as you see, the kink is not really a very sharp point. It's a gradual bend. So you might ask, what am I calling as the kink? Another interesting thing that happens is that there is also a sharp drop in entanglement near the kink. So what you can do is you can calculate this quantity called entanglement power. And this is a kind of a measure of how entangled the final state particles are. And as you can see, here I've plotted it not against S naught, but I have plotted it against a physical quantity, the S wave isospin 0 scattering length. And this is what the various S matrices do. So you start off on the left-hand side of the river. And as you go down, suddenly near the kink, it suddenly drops. The entanglement power drops. So it's as if it loses entanglement as you approach this kink region. And then it exhibits a very interesting trajectory in terms of the A0 plane. So unlike the total scattering cross section, which was averaged over a large range of cutoff values, here I've shown you the plot which is only at low energy. So this is what you get for the entanglement power at S equal to 4.01. So definitely, so what we conclude is that there is something special that happens near the kink, and definitely it appears that there could be a selection principle. Maybe one selection principle could be that the standard model S matrix should be the one that exhibits the sharpest drop in the total scattering cross section, or the sharpest drop in the entanglement in this neighborhood. There's also a puzzle. So as I told you that there are two regions, not only near the chiral perturbation theory, what we get a region which is close to the chiral perturbation theory point. And of course, that's great, because chiral perturbation theory does not give you Regé behavior. You have to do something different to get Regé behavior. So the S matrix bootstrap, numerical S matrix bootstrap tells us what to do. But there's also the second region, which is in this lower boundary here, near here, which also gives us the same kind of experimental results. We get reasonable Regé trajectory, we get reasonable F0 meson, we get reasonable scattering lengths as well. So which one is the correct standard model? So we don't have a definitive answer to this as yet. So one thing is that the upper kink exhibits the sharpest drop in scattering. So the drop, you get sharp drops both for the upper kink as well as the lower kink. The upper kink exhibits the sharpest. So in that sense, you can say that, okay, so that sort of selects out that region. And also in some sense, and this is a kind of back calculating, because we know the chiral perturbation theory answer. So this is closer to chiral perturbation theory in the geometric sense. So the S0 S2 value is closer to the chiral perturbation theory. So maybe that is the region, but we don't have a definitive answer to this point as yet. So it's still a puzzle to us. So one thing that the upper kink and the lower kink do differ is in the value of the effective ranges. So the effective range B02 for the lower kink is substantially different than what you have in the upper kink. And so maybe if there were some experimental results, then that would definitively allow us to compare and check which one is a better S matrix. But the bottom line is that the standard model appears to satisfy interesting properties. It gives you some interesting geometry on the allowed space of S matrices. Maybe there will be a selection principle which will non-perturbatively select it. So it will be good to play with information theoretic ideas which will enable us to answer this question. But one important thing is that we will definitely require a version 2 for the numerics, because one thing that happens, and that's what we have observed, is that the imaginary part of these resonances, the widths, they have slow convergence. So we want a different basis. We need a better basis which will exhibit faster convergence so far as the widths are concerned. And I can tell you that these numerics, the way that things are done right now, they are extremely slow and painfully slow. You cannot do things on a laptop or a desktop. You really require powerful clusters. Without these powerful clusters, you will not be able to do it. And it is our hope that these numerics will become better, because we can then probe very interesting questions faster. But definitely one can be optimistic that, like the 3D Ising model in the CFT bootstrap, one can also do precision phenomenology with the standard model bootstrap. And this may be a way to also probe connection with string theory in a systematic way. So I should conclude by telling you a little bit about Indian Jugaad. So all this work was done during the time of the lockdown. So of course we wanted a Harley Davidson, and but Indian Jugaad is that you have your version of the Harley Davidson. So these are literally boots making up the bootstrap. So this is quite poetic. But because we don't have these, the resources are limited, maybe necessity here will be the mother of invention as well. But I should definitely say special thanks. We did not have good computing facilities when we were doing this. So I should thank RRI for providing us with a powerful workstation, which enabled us to do some tests. But maximum thanks goes to the ICTS folks, which enabled us to develop these numerics to the level where we have reached. So this is Rajesh, Samriddhi, and Hemanto, and they were very nice to us, and they provided us cluster access that enabled us to perform these numerical experiments. And I should, as I said, as things stand, without powerful clusters, these numerical experiments will lead to an increase in mental health issues in these already troubled times. So I think this is an opportunity to develop better things. And I should close there. Thank you.
Okay, so the floor is open for questions. I have a question. How much of the standard model inputs have you put into this computation? I mean,
very little.
Very little, right?
Yeah, very little. So only the row resonance mass, and so I'll. So these are the only inputs that we have put in.
Mm-hmm.
So this is these are scattering length inequalities. These are not standard model inputs. So the D waves are, it's a dispersion relation inequality. It has got nothing to, this has got just nice behavior that arises from dispersion relations. So any good theory is expected to satisfy the first line. The second line is what we would expect from a Lagrangian approach. And the essential standard model input that we have put in is the mass of the row resonance, including the imaginary part.
What would happen if you added one more resonance?
Could I ask a question?
Yes.
Yeah, David, I think is, yeah.
Go ahead.
You mean by expected from a Lagrangian approach? What does that mean?
So I'm assuming that there is a chiral perturbation theory kind of Lagrangian. So if you did the tree level calculation, these are the sign inequalities that you would get, and these are of course respected also at higher loops. So these look very similar to the D wave inequalities, but I cannot derive them by demanding a dispersion relation, because the dispersion relation requires a certain number of subtractions.
Right.
Yeah. Did that answer your question?
So by a Lagrangian approach, you mean chiral perturbation theory plus some limitation of higher.
Yeah. So
higher dimension.
yeah. So So chiral perturbation theory, tree level, one loop and two loop, all of them respect this these inequalities. So, so that's what I essentially mean, that if you have a Lagrangian-based approach, say chiral perturbation theory, then perturbatively these inequalities are respected. So I'm not putting in these values, I'm just using the signs.
I see. Okay.
Are there any other questions?
Yeah, can I ask one?
Yes, yes, please.
Yeah, so in QCD, one of the bits of trick we do for dealing with the subtractions is by using dimensional regularization. You can set things up so that you don't actually need the subtractions.
Yes.
Would a trick like that, and since you were complaining about the subtractions,
yes.
So there's a paper from Van Eerven that I can point you to.
Oh, that would be very, very nice. I mean,
yeah, but Zvi, this is non-perturbative.
But still, the issue of the reason you need subtractions is because something is not converging. I mean, there's some integral.
Just the amplitude isn't, doesn't fall off fast enough at infinity to write an unsubtracted dispersion relation.
Well, but we do that. Well, I can point him to a paper and he can see. I mean,
but you're discussing amplitude, perturbative amplitudes that show. He's not assuming, he doesn't have a perturbative expression for the amplitude. He just has unitarity and analyticity. That's all. So he has to know, and the asymptotic.
Sorry, I lost you there.
Yeah, David, we lost you. Can you repeat?
Yeah, somehow the internet.
Zvi, this is not a perturbative relation where you have a definite you want to calculate. He's just using analyticity and some asymptotic behavior, which is not enough to write unsubtracted.
But there's some integral that's not converging. And
yeah, well,
you would think
it's not
with an appropriate analytic continuation, you can dance past that. That something isn't dropping off fast enough at infinity. And this type of trickery is that's what it is. But I mean, it's also possible. I need to look at the details of what the problem is. And I can just point to a paper, and then he can tell in 5 minutes if it helps him.
Okay, sure, and that will be very, very nice. I mean, we were looking for some argument which would enable us to impose these S-wave inequalities, but we couldn't find any. I mean, there is another way to motivate these S-wave inequalities, which I did not have time to explain, that uses properties of relative entropy. So it seems like if we impose these signs, then we would get some definitive sign properties in relative entropy, which we felt was a nice thing to have, but I didn't have time to explain that. So any other questions?
Aninda,
yes.
Can I ask a question? Yeah, so these quantum information theoretic ideas for measuring the closeness, can you motivate why that's the natural sort of way in which you should measure closeness?
Yeah.
And even the previous one that you showed on the river, using the relative entropy, yes.
Yeah, so So you wanted why we are using quantum relative entropy as opposed to something else? Is that your question?
I mean, I mean, you could think of many possible measures, I guess, in the space of S matrices, or.
I mean, this is so. I think the best way to ask is that it is related to how this statement that I made here, which I think is best explained in this review by Edward Wheaton in 2018. That if you want to say with confidence, with what confidence that you, after n measurements, you have different different theories, different hypotheses, T1 and T2. So this is actually governed by this quantity 2 to the power minus n times this d. So this d is the quantum relative entropy. So this is also motivated by what follows from classical information theory. So here you'll have a same kind of quantity that appears using what is called the Kullback-Leibler divergence. So that is something that arises from classical information theory, and you have the same kind of property also for quantum density matrices. So this tells us that if you have a larger this quantum relative entropy, then you'll require fewer number of measurements. So that's what will enable you to distinguish two density matrices. So does that kind of answer your question?
Yeah, no, it seems like a good measure. I was just wondering if the answer, because you have this kink, I mean, you have this sort of river, and you want to be sort of sure that that whatever measure you use, anything reasonable, should not qualitatively change your results.
Yeah, that is true. So you mean that why? Maybe I can paraphrase your question and say that why are we having such big green regions? Why don't you have something smaller? So okay. So one thing is that I probably did not emphasize enough is that when we did this calculation, we were focusing on the low energy region, so we were close to S equal to 4. But maybe if we did an average, then it would be different. So in our context, the measure, of course, depends on S. We are integrating over X, but it does depend on S. So S is not integrated over. So it does depend on what value of S we are using. So this is something that may be considered. And in fact, I think it's worth considering if you average over S, what you get.
Can I ask another comment?
Yes.
So, very interesting talk. Since you referred to a paper I wrote on the road bootstrapping the road trajectory.
Yes.
You know, at that paper, actually, I looked not at pi elastic scattering.
Yes, you looked at pi omega. Yeah.
Pi omega, which was also studied by the group in Weitzman. And then Gabriela went off on the boat and discovered the beta function, which solved that problem and gave birth to string theory. I always kick myself for not knowing about the beta function. But anyway, the pi rho omega was chosen because it had isotopic spin 1 in each channel, S, T, and U, right? And so there was only one amplitude. You got rid of all the problems with the, the I equals 0, 1, and 2 mixing. And farther removed from experimental study. But it theoretically a lot simpler because there's only, only the rho channel in both ST and U. So you might find that easier to analyze as a theoretical problem.
Okay, thank you. Thanks for that comment.
Are there any more questions? Otherwise, let's thank Aninda. And this session comes to an end. The next session starts 1.5 hours. No, 2.5 hours from now at 2 p.m. Indian Standard Time. Okay, but thank you, everyone.